So thank you. Today our presentation topic will be about a tensor network, which is basically a core topic in quantum machine learning. Today we will discuss about that network. Where in this presentation, I will try to cover all the basic info about tensor network as well as uh, an experiment which I can optimize by a tensor network in a model. So let's start. So first, our presentation outline will be as what is tensor and the tensor network. In this presentation, I will try to describe about the graphical representations of tensor network and how the tensor network actually connected with machine learning. And as tensor is all the combined model. So how the model can be decomposed as we want, if we want to optimize some kinds of model, then we need to decompose that tensor. So here we will also describe about different tensor decomposition techniques, and finally I will propose or describe about a algorithm which can be adaptable for any kinds of tensor network structure. So the basic things will be how a tensor network can choose their the tensor decomposition technique so that they can optimize by their self. That's called self learning. So here we also discuss about later. So first of all, we will start about what is the tensor. So as you can see, there is a very general definitions of tensor, but I will start with the graphical representation. As you can see, we all know that matrix is a two-dimensional array of numbers. So here M is a matrix which have two indices D1 and D2. So matrix will be belongs to a real number. So and what is basically a tensor? So mm, first of all, when we talk about a matrix, then we another things comes in our mind, that is what is scalar, what is vector. So scalar is we know is the only represent the magnitude, but vector is all not only magnitude but also the directions, right? So so we in the next slide we'll show about that. But tensor is a multi-dimensional array of numbers. As you can see, is a three-dimensional representations. This tensor is yeah, the three-dimensional as we said. The three indices like D1, D2, and D3. So now we will talk about the how the tensor is connected with machine learning. As we know that our real life data are organized like distributed data, right? So tensor try to find out some pattern from that distributed data, and that's the core side that connect the tensor with machine learning. So we can say that data of course has a tensor structure, some like color images or multivariate time series video, any kind of data can be, it could be. So another thing that is tensor can also used as a parameter of a model, right?
Yeah.
Video this. One. Sorry. So the tensor can also used as a parameter of a model, like polynomial regression, higher order RNNs, weighted automaton trees, and graphs as well. Like how tensor we used in a model, like uh, so we will describe in the letter like how the tensor can be used as a model. So so to describe about the parameter, how parameter is used in a model, we have to learn about the basic calculations of the matrix or any kinds of uh, like tensor. So here, as you can see, that matrix and the matrix M, and there is another two kinds of matrix, A and B, which is the same number, which has the same number of rows and columns, and M can be multiplied both in both directions, like A and in B direction. So we can see that, like you can see that matrix A, matrix M, matrix B, which is the transpose of matrix B, all together can be multiplied, which will be greater than the indices. So here is the multiplications of tensor with another three matrices, like you here it are three matrices, matrix A, matrix B, and matrix C. So these are also, as I said, that these all the matrices are the same number of rows and columns, otherwise it cannot be multiplied, as you know. So here is I can see that the tensor is multiplied mode 1 of A, and mode 2 of B, and mode 3 of C. So as you can see that here is the is a great calculation, big calculation actually, but if you can concentrate on the calculation, you will find it very easy, like sorry. So here, as you can see that tensor matrix A, B, C are all together multiplied, and we have number of summations all together. So as multiplication could be done with this procedure. So here we will talk about the tensor networks in a graphical representation. As previously I said that vectors, about vectors and a scalar, but here you can see as a node that we call a vector, which has one open leg or an S, which has D weight, and here is the matrix, which has two open S, which is called M and N, and tensor. Tensor is a multidimensional array. So what is the point from this graph is that the number of degree of a node will be equal to the order of a tensor. Like we know that the what is the degree of a node? That is incoming and outgoing is number of incoming and outgoing is, right? So a tensor of order will be like that. So whenever you would represent a node, then the incoming or outgoing number of is will be the order of that tensor. Okay, so so here how can we in this we already discussed about how the matrix can be multiplied, but here we'll talk about how when uh, two or multiple types of nodes are connected, then how the productions is actually works. So as you can see, here are two A and B, two matrices, and A and B has two different open A's, but it has a connected S, right? And so what is the term it called in tensor? That is contraction. When the two A's from the two different matrices is connected together, then it is called contractions. The as you can see here, AI1K, that is from the A matrix, the last indices K is connected with the matrices matrix B. Okay, then so what is called this type of S we will call in tensor network, that is S. Okay, so yeah, so here we will talk about the inner production and the inner production between two vectors, or inner production two tensors. Later we will talk about inner production between two same kinds of tensors. Here first inner production is only between contraction. So yeah, previously we have seen that two matrices had two open legs, open A's, but in here there is no open A's, right? So there is a connected A's N. So here is a simply multiplications of U and V, and the result of will be the summation of that multiplication. So inner products between tensors, here as you can see S and T, two different kinds of tensor. This could be like S could be more than three dimension of array, and T could be 4-dimension of array, but two different kinds of tensor are connected each other by three contract indexes D1, D2, D3. Altogether are multiplied with that D1 number or data set I1, data value of data I1, I2, I3 from D1. Okay, D2. So the I4 okay, is okay. So the all the value from D1, D2, D3 will be multiplied with S and T. So here comes about another when two tensor. Previously I said that two tensor are different dimensional, but in the Frobnius norm of a tensor, we can see that tensor is the same dimension, right? So here we can see that these two types of tensor has same type, same number of what would you say, same number of dimension. So we can see that it's a formula. There is a reference, of course, how actually it works. So next one is trace of n by n matrix. So what it happened that it's a matrix, and it has a circle with n by n matrix. In trace matrix happen that there is no open edge, and the edge is connected by itself. So there is another kinds of tensor networks. So it's a very basic of tensor networks. Then it's the tensor time matrices. What happened where here one tensor T is connected with other three matrix A, B, C, which has the different what would say different directions, and A has data with M1, B M2, and C M3. So all tensor times matrices in this is a very basic. I already it's a combinations of the previous graphic notation. So here is the one term that is a new very hyper S. We already know about the contraction. When two free S is connected together, then it is called contraction. But hyper S is when more than two free S are connected. So here is the hyper S, UV. So the three matrices UV and W, and the three S's are connected. So this type of connected is we will call hyper is. So here, sorry, is here all about the tensor networks. It's a very basic of tensor networks. If anyone want to know tensor network, then he or she had to know about that, about these simple types of networks, right? So now we'll describe about how tensor could be decomposed. There are a lot different kinds of tensor decompose technique, but our idea will be we will decompose a tensor with some smaller number of factor, right? So there are already different techniques, some of them. So we will start from the Tucker decomposition. Taka decompositions means previously we described about how a tensor and how a matrix is a multiple number of matrices are multiplied together. But in these decomposition techniques, when it's a three-dimensional, basically in this presentation we'll describe about three-dimensional tensor. So tensor T is decomposed into U1, U2, and U3 matrix. So here is you can see that the parameters are all multiplied and then summed instead of D1. So there another decomposition technique is Taka decompositions. So Taka decomposition is basically general form of uh, 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 sorry, the Taka decompositions. Here is the another representations of you can represent also previous tensor in the graphical notation like this. So it's the same calculation. Now we'll discover about CP composition, decomposition. So CP decomposition here, CP decomposition is the general form of Taka decompositions. Here we, as you can see, here is a hyperedge like U, V, and W. There are three A's which has the similar parameter R. They are all together connected, and here X sorry. So first of all, we start from that left side graph, that is X. It has three A's, D1, D2, D3, and whenever we decompose that tensor, it will like UVW, and it will have the same parameters R. So there's the reasons we have R multiplied with D1, D2, and D3 summation. So here we will not multiply D1, D2, D3. Here all the indices will be summed. So here another decomposition technique is tensor train decomposition. So it's also said that chain decompositions. Tensor T, it has 4 open A's, and tensor is G 4 tensor G, and each two tensor connected with its parameter, and one is open. So the calculation will be like that, as same as previous one. But here we here is some exceptional case, like all the parameter will be equal, like as you can see that tensor T are equal as. So the vectors of the we can represent the vector as 2 power n. Okay, so if in here we describe about that if we decompose a decomposite tensor which has multiple A's. So here we can see that the if from one tensor we have multiple A's, then sorry, I will skip it. Then tensoring decompositions, there are four A's that when we decompose it, we will get Z1, Z2, Z3, and Z4. Each of them are connected with each other, G1 with G2, G2 G3, and G3 with G4 and with G1. So here is a circle, as you can see, and each tensor has its open indices. We have similar to the tensor of composed tensor. So the calculation will be here given. So that's the basic of tensor decompose techniques. So here I cover the graphical notations of all tensor networks. These tensor networks will be used in the uh, complex operations of tensors. And another one section was tensor decompositions. So here tensor decomposition, it can also be used in neural networks, and whenever we try to when we have multi-dimensional data, we can compress it by using the tensor decomposition technique. So, uh, the tensor network methods can be used in very high dimensional objects, in machine learning, we also the principal component analysis network. So, in a tensor network, there are lots of problems, but here we will describe about a greedy algorithm, which is adaptable. So the new things here, we say that all the linear algebra are is becomes whenever all the computations or calculations occurred in tensors, then linear data can be also multilinear data can also be calculated from the tensor networks. So, the questions will be from the basic types of tensor network is whenever uh, like you have given a problem, and you have to choose a decomposition model. So how the problem will choose that decomposition technique, that this decomposition will give me the best optimized value. So it could be one problem, how right decomposition model could be used in ML problem. Here two types of two techniques can be used. First of all, we can fix the decomposition technique, that only this technique method will be used in this ML problem. Another one is ML problem won't select the decomposition technique. Okay, so that's the thing. So in artificial intelligence era, we have to choose that model that shows itself that this method will be perfect for me. Using this decomposition technique, I can optimize my given problem that is at hand, right? Whatever my problem is given to me, I can choose any types of given method, that this method will be appropriate for me to solve this problem with great efficiency. That's the problem. So another thing is, okay, uh, so we will describe about a very naive method, which is a model will learn from that data that is it can the very beginning of my presentation, I said that all the data are scattered. So whenever machine learning or any types of models get uh, training data from itself, so that time that model could also be uh, like this model also be independent to choose that what decomposition technique or tensors others like models can be used. So my thinking is that how it could be like is in machine learning AI we would say supervised learning, or that's the thing we can use in it. So there is another thing that is uh, that is also goes with the AI, where the data will not be biased, right? Each and every individual should be equal priority. That's the main thing. So uh, how the if the bias, implicit bias, how uh, it could be encoded in is decomposition model. So here is the three questions. So we will discuss about a greedy adaptive algorithm which can self-supervise it, how actually I chose the right decomposition model. So I took this idea from one of professor which is uh, who is working on quantum machine learning. So I took idea from him. So that's he also to say that that idea is very naive. So I will describe it. So was what will be the how the problem will be optimized. First of all, we have to calculate the loss function. If we could minimize the loss function, so the model could be optimized, right?
Yeah.
Loss, if we want to optimize any kinds of model, first of all, we have to not only tensor but also any kinds of model, we have to calculate the uh, error and we have to minimize that error. In tensor, we have to minimize the loss function. So as I have seen in all the previous very basic the structure, that is all about node. It's all about all the nodes are connected. It's all about how the nodes are connected, how the weighted is are free. So if we can formulate that structure in a proper uh, method that can minimize the loss function. When our main target is minimize the loss function. So in that case, we also see that here is a basic of all the mathematical term, but I'm trying to say the basic concept. Yeah, what I understood from the from his lecture actually. So yeah, it's as you can see here is given a equation term, that is LW. L is a loss function, and tensor rank is given tensor train, tensor ring, CP, all kinds of decomposition technique. So main thing is we have to minimize the loss function. So here is another thing, that is tensor completion. Now what is actually is you have given an image. So image is a image, as you can in two-dimensional image, it is a vector, right? So whenever we uh, uh, use an image as a input, so there may be some unnecessary pixel or unnecessary value. So we will pick some data, some pixel that makes some pattern, right? That makes some pattern. Otherwise, all the pixels are useless. If we can, like, if we can choose that pixel with some value, weighted value, and if we could ignore some unwanted pixel, so we automatically can optimize that method technique, right? If we could choose here is the first. So as you can see, here is a butterfly. So our main object will be extract that butterfly. As you can see there, in background there are some green pixel, like suppose green pixels and some flower. So if we want to extract that butterfly, we have to focus on that pixel, and we have to ignore all the background pixels and the flower pixel, right? If we want to extract butterfly. So our main thing will be to give weight is some to give some weight into that pixel, so we can easily extract that pixel and ignore other pixels. So if we could make that, so the loss the processing time or memory, the other we need, so it will be minimized. So the automatically the optimization technique will be minimized. The other in another word, we can see that loss function will be minimized, right? So here is the basic thing. He described it very nicely, but I don't know how I make you understand. So that's the thing. And we here is a, so how the gradient algorithm actually works. So first of all, we start from the like uh, what happened in neural network. Neural network, we give some input layer, some hidden layer, and output layer, right? So in tensor, this greedy algorithm will start from a core tensor and calculate some loss functions. So whenever we decompose it, then we have multiple types of loss function, and among them we have to pick the best best proposed minimized loss function, or the lowest minimized function, right? So here is the that's the main thing. Other all the branches are like I don't know what, but the best thing is we have to pick out the lowest minimized function, and that branch will be extend in another multiple types of branch. Here it could be 3, it could be 4, and from that 4 or 3 tensors we will uh, again we will choose lowest loss function. This will repeat until we get the our desired loss functions. That is will this method the threshold loss function. So here is a, so he proposed a greedy approach, and one with a rank one tensor. So uh, all I have said what have this in here written. So here is the tensor. As the first in the from my presentation, I have described about the rank. So here is you can see that first order tensor. The what he described about, he not simulate that model, but he used that loss function 0.9 as an example. He and his team members are trying to simulate that model about 4 to 5 years ago. I don't know he has completed it or not. I mailed him, but he didn't reply. So whatever he told in lecture, so I'll describe it. So let's say the loss function is 0.9. Then we will connect two nodes together. As you can see, the first in the first perceptron there the two no node are connected, but here two nodes are connected. So then the loss function is 0.5, and 2 and 3 nodes are connected. Let's give weight 2. There is 0.2 loss functions, and if we connect 1 and 3 nodes, the loss function will be 0.4. So as you can see, the minimum loss function is 0.2. So we will extend this branch and ignore all other branch. Okay, that's the main thing. We will calculate loss function. So Here is another thing that we described about it with 3 nodes, but it can be thousands. So uh, 3 nodes is 0.12, and all the 0.12 that, as you can see, that node 1 and 2 is connected, node 1 and 3 is connected, and the loss function is 0.15. So here is, as you can see, the 0.12 is the lowest loss function, so it will uh, extend its branch, ignore others one. So it will extend until we get our threshold loss function that we have given. So that's a naive method, he already said, but it has some limitation, of course. The limitation is you can not, whenever it's a, like we have read that in software engineering, like water flow model, like if you go step forward, you cannot back. So whenever we set a loss functions, that's fixed, and you will step forward, and you can update that layer, but not backward. That's the thing you cannot do in this naive method. Another thing that is this naive method will only used in contractions and 1s, but not in hyper-s. I already told what is hyper-s, so that not will work in that. So that's the limitation. So my all the presentations is this Dr. Guillermo Rabosia professor. He helps me actually by giving some information. So I try to make some slides. So that's all about. Thank you. I don't know how how I later make understand, but that's all about. Thank you for patient by
Yeah, thank
hearing.
you for the presentation.